Hello everyone, I'm Thinknyx speaking on behalf of Thinknyx Technologies, and I'm delighted to have you with us for another informative tutorial. In this tutorial, we will explore the concept of cloud native and delve into its guiding principles. Achieving a cloud native architecture is frequently regarded as the ultimate objective when embarking on application migrations or new developments in today's landscape. You have probably come across the term cloud native before, but let's understand what does it mean. In simple terms, cloud native refers to a modern approach to building and running software applications that are designed to fully leverage the capabilities and benefits of cloud computing. It's about creating applications and services that are specially optimized for the cloud environments. A cloud-native application is meticulously crafted from the very beginning to leverage the inherent capabilities of cloud technologies such as dynamic scalability and distributed infrastructure. These applications are purpose-built to unlock a spectrum of advantages, including remarkable speed, agility, scalability, reliability, and cost-effectiveness for organizations. The fundamentals of cloud-native architectures are rooted in several core principles. These principles form the foundation for building applications that fully utilize the benefits of the cloud for any organization. Some of them are modern design, microservices, containers and orchestration, DevOps, CI/CD, and automation. Now let's discuss these principles in detail. Let's start with modern design. Designing and deploying cloud-based applications, particularly in a cloud-native framework, can be complex. The 12-factor application methodology lays out crucial guidelines for building efficient cloud applications. These principles were originally introduced by Heroku, a cloud platform as a service provider, and have since become a widely accepted standard for designing cloud-native applications. Each of the 12 factors addresses a specific aspect of application development and deployment. For example, the code base factor says use one central place to store and manage your application's code. This code should be tracked and versioned using a tool like Git. Multiple instances of your application can use this same code base, ensuring that they all have the same source code, which is vital for consistency and reliability. Next, let's take build, release, and run factor. This tells us to break down the deployment process into three distinct stages. Build. Create your application from source code and dependencies. This is like building a house from blueprints and materials. Release. Combine the build code with configuration to create a deployable package. Think of this as furnishing and decorating the house. Run. Deploy the release package to your server. This is like placing the fully furnished house in its location. Separating these stages make it easier to reproduce deployments and if needed, undo them, just like you can move furniture in and out of the house without rebuilding it from the scratch. We highly recommend visiting the official website 12factor.net to gain a comprehensive understanding of the 12 factors. Each factor is explained in detail and you can click on the individual links to access more information about each one. This will provide you a thorough grasp of the 12 factors and their significance in the modern software development. To simplify this process, cloud providers offer well-architected frameworks that supply industry-standard best practices. These frameworks help teams construct resilient and high-performing cloud solutions, allowing them to fully leverage the capabilities of cloud technologies. In this context, the image could feature well-known public cloud providers such as AWS, GCP, and Azure. However, it's also worth considering other valuable alternatives like DigitalOcean, Alibaba Cloud, or even private cloud solutions such as OpenShift. These diverse options cater to various needs and preferences in cloud infrastructure and services. Before we proceed, let's grasp the concept of two distinct architectural approaches, that is monolithic and microservices. A monolithic application is a single large code base that contains all the components and functions of the application. Imagine building a monolithic e-commerce website where all the code for the product catalog, user management, payment processing, and order fulfillment is contained within a single massive code base. In this monolithic design, all the code is tightly interconnected. If you want to make change or update, you typically have to modify the entire code base. This can be complex and risky process, often leading to potential downtime of the application. This approach was commonly employed in the past. It's like trying to renovate a large interconnected building without affecting the whole infrastructure. In contrast, microservices architecture breaks the application into smaller independent services, each with its own code base and responsibilities, including managing its own database. In programming, this could mean having separate microservices for product catalog, user authentication, payment processing, and auto management. Each microservice has its own code base and can be developed and scaled independently. In this microservice design, each component is like a standalone program that communicates with others through well-defined interfaces, usually APIs. This makes it easier to update, scale, and maintain each service without impacting the entire application. It's like having a collection of small modular buildings that can be modified or expanded individually. Microservices offer a significant advantage in creating a minimal viable product by enabling development of small independent service components. This approach allows team to focus exclusively on essential features, streamlining the MVP's development process. As a result, it becomes easier to iterate, test and launch MVP quickly, meeting initial user needs while maintaining flexibility for the future enhancements. Cloud native systems make extensive use of microservices, which are like building blocks. They break applications into smaller manageable parts, ensuring flexibility and adaptability in the ever-changing cloud environment. This approach simplifies development, scalability, and resilience, which are all the crucial aspects of cloud native systems. Containerization plays a pivotal role in the cloud native ecosystem by simplifying the deployment and management of applications, making operations more straightforward and efficient. Cloud native containers are lightweight, self-contained units that encapsulate an application, including its source code and dependencies. They embody the build anywhere, run anywhere philosophy, enabling developers to create applications that can effortlessly transition between various cloud environments, streamlining the development and deployment processes. Across various industries, there is a common misconception that cloud native solely revolves around the containers, but this isn't the case. While containers do play a substantial role in development and hosting, they are just one of the components of the broader cloud native ecosystem. Cloud native encompasses a more comprehensive approach to building and hosting applications, with containers being a vital element within this framework. In a cloud native context, container orchestration plays a pivotal role as the number of microservices and containers increases. Platforms like Kubernetes act as essential orchestrators, ensuring the smooth operations of containers within cloud-native applications. They offer centralized control of container placements, automated recovery from failures, and load balancing, all contributing to the effective and resilient execution of cloud-native applications. Additionally, Kubernetes facilitates both horizontal and vertical scaling, allowing applications to dynamically adapt to varying workloads and ensuring demands. Cloud native applications with their microservices and containers introduce challenges like deployment complexity and version control. DevOps practices are crucial to bridge this gap by ensuring efficient, reliable, and secure cloud native application delivery. DevOps achieves this by automating CI/CD pipelines, which accelerates deployment while reducing errors. It actively promotes the adoption of infrastructure as code principles, ensuring consistent and automatic resource provisioning. In addition, DevOps places a strong focus on robust monitoring for real-time issue detection, all while seamlessly integrating security and compliance measures into the development pipelines, with automation as the key driver throughout these practices. Collaboration between development and operations team is encouraged, breaking down silos and ensuring cloud-native applications remain agile and stable amid evolving business demands. The Cloud Native Technologies Pyramid is a model that illustrates the different layers of cloud native technologies. The bottom layer of the pyramid is containerized hosting, followed by microservices architecture and CI/CD enabled DevOps processes. The Cloud Native Technologies Pyramid can be used to guide the design and implementation of cloud native applications. By understanding the different layers of the pyramid, developers can choose the right technologies for their specific needs. This pyramid shown provides a fundamental structure, but it's highly customizable to fit to an organization's specific needs. It can be expanded with additional components and layers to align with the organization's unique requirements and goals. As we conclude, we extend our gratitude for tuning in and joining us on this journey to understand cloud native and its guiding principles. Please do like and subscribe and click on the link below to know more about Thinknyx. Thank you for your time and attention. Wishing you a wonderful day, and we eagerly await your presence in our future content.